Hello everyone, this is Roy PCB, your trusted PCB partner. Today my topic is power integrity in 6-layer PCBs. Power integrity and its causes. In complex electronic systems, we not only need to pay attention to whether the data on the signal lines is correct, we also need to ensure an even more fundamental but equally critical issue, the health of the power supply. This is what we call power integrity. Today, let's talk about this topic. Can power supplies also have heart disease? And what negative effects can power supply ripple and ground bounce have on our design? First, let's take a look at our program today. In the middle, this is a high-speed CPU, and there are a lot of capacitors attached behind it. This is because these high-speed chips have very high requirements for power integrity, so they are equipped with many capacitors of different sizes. In the schematic, we can also see that this is its power supply section. The power supply section is equipped with a large number of capacitors, and at different voltages you have capacitors to ensure its integrity. So what exactly is power integrity, and why is it so critical? What is power integrity? It refers to the power distribution network on the PCB being able to maintain performance even when the load changes dynamically. It provides all active devices with a stable and low noise power supply. In simple terms, the ability of the power supply voltage is to ensure that your power supply chip gets clean and sufficient food. Why is this so critical? First, it ensures the stable operation of the chip, especially high-speed digital chips, which during rapid switching can draw large currents instantaneously. If the power supply is unstable and the voltage fluctuates too much, the chip may not function properly or could even crash. It also ensures signal integrity. An unstable power supply will directly affect the reference voltage for signals, thereby degrading signal integrity and causing false triggering of signals. It can also create EMI/EMC issues, as power supply noise and ground noise themselves are major sources of EMI. This may cause the product's radiation to exceed limits and affect EMC certification. Let's take a look as well. This is the power supply measured with my oscilloscope. What we usually see is more like the upper trace here, which is at 500 millivolts per division. It looks like a straight line, but in reality, the power supply isn't like that. Look below. When you zoom into 5 millivolts per division, you'll see it's not a straight line. There is a lot of noise. We can't provide a perfectly flawless power supply that becomes a razor-thin line. But in circuit design, we need to ensure that this noise is kept to a minimum. Power supply noise is caused by ripple and ground bounce. So how do they contaminate the power supply? In a power system, there are mainly two sources of contamination. The first is power supply ripple. Its main generation mechanism comes from the power converter, such as DC-DC converter. These are caused by high-frequency switching actions or by voltage fluctuations generated when transient current demands from the load pass through the power network impedance. The main harm is that it affects analog circuits and through coupling impacts digital circuits, increasing signal integrity issues. What we see below is the power supply. Every power supply has ripple. It's just a matter of how much. The more tightly we control it, the smaller it becomes. Next is ground bounce. What causes ground bounce? It occurs when a large number of digital gates switch states simultaneously. This causes a sudden surge of current. As this current flows through the ground plane, the inductance of the ground plane generates a momentary voltage rise. This is ground bounce. Its main harm is that ground bounce can cause reference level instability. This causes the chip's input signals to have their reference level raised, which may lead to false triggering or functional abnormalities. We can also take a look at what ground bounce waveforms look like. The waveform below is ground bounce. Normally, it can be considered as a fluctuation that is very small. The line here is the ground line, which is at zero output. When the logic gate switches on its edge, either the rising edge or the falling edge, the rising edge produces a very small fluctuation, while the falling edge produces a much larger one. This indicates that the falling edge within the circuit will create such a fluctuation on the ground potential at the edge, which is called ground bounce. This results in instability of the ground line's potential. What are the inherent shortcomings of four-layer boards in terms of power integrity? We know that four-layer boards are usually designed as follows: signal, ground, power, signal. These are the typical arrangements. They are much better than double-layer boards, but when faced with extremely complex power requirements, there are still limitations. First, there is only a single power plane. If the board requires multiple voltages, this plane must be partitioned, which increases the complexity of the power network and may disrupt the continuity of the power plane, weakening the plane power effect. Secondly, the coupling distance between the power and ground planes, even if you have both power and ground planes, the distance between them may not be close enough. This makes it impossible to form a very strong plane capacitance to suppress all high-frequency noise. Lastly, there's the return path. The return path for high-speed signals is usually the ground plane. If the ground plane needs to provide return paths for multiple power supplies and is segmented, the return path can become complicated, affecting power stability. Today we learned about the importance of power integrity and the impact of power and ground plane noise on design. We also gained an initial understanding of the limitations of four-layer boards when dealing with complex power requirements, and it is precisely to overcome these limitations that six-layer boards and boards with even more layers are used. This provides us with more robust power integrity capabilities. In the next video, we will delve deeper into how to design multiple power planes on a six-layer board and how they can significantly enhance the stability of the power network. If you enjoyed this video, please subscribe to my channel to get more videos. Thank you all.